Okay, take off. Yeah. We met once.
Yes,
You're waiting for it. Yes. Actually, I met your collaborator in McMaster, right?
Andrew Nick.
Yes, right. Yeah, I visited once this in Hamilton. Yeah.
Yes, right.
Talk's over, right?
So, I'm happy to. We're happy to welcome Fuquan Fang from Capital Normal University, and he's our first speaker of the semester, and he will talk about reflection groups, non-negative curvature, and Tits geometry.
Thank you. Yeah, it's my great pleasure to be here again, and thank a lot to Tom and Pedro, and it's very nice to meet another friend. To my surprise, I met Stratos. I think we were together maybe over a dozen years ago, right, in Brazil. Yeah, so very nice. So what I'm talking is that joint work with custom group and Topology is something related to remaining geometry, but also related to geometry topology. So basically, when I talk about the three looks on the face, looks very different topics like reflections, which is the kind of very basic symmetry, and non-negative curvature. What I mean is like remaining curvature, or means sectional curvature, and remaining manifold. And the Tits geometry is sensitive. Tits geometry is a kind of very powerful machinery in algebra, like group theory, even related to chaotic group, negative group, and number theory. A kind of combinatorial object, by the way. Okay, so let's start with some very standard things we call a discrete group generated by reflections in the Euclidean space or affine space. That's what we get is kind of Euclidean reflection group. That's what I mean. Which, of course, we are very familiar. For example, consider the symmetry group a regular polytope in the Euclidean space, or we may consider a tiling of this Euclidean space by some congruent copies of regular polytopes, which this will give you a reflection group, which is very familiar to us. Of course, this kind of very important example as this kind of reflection group are Y groups or crystallographic Cox groups, which plays an important role in D theory, as we know. And for example, here is a very standard example of the Cox group or the Y group of SU3, right? So, which is really just the reflection group in R2 generated by two walls, right? By H1 and H2, right? So this is nothing else, just the Cox group of SU3, and also which is just a dihedral group for the 6. And for example, if we have a tiling of by this equilateral triangle in the R2, what we get is this infinite group which contains this lattice. You may see one lattice there. I consider the random two lattice as a cofinite group where with the quotient to be the final Cox group. So this, the whole group, we call Darwin 3, where the Cox group associated to a cosmology algebra, right? We know that. And here is another tiling, for example, for the R2, where it is tiling by another right angles, where with angle, one is an angle, right angle, another is an angle pi over 3, another angle is pi over 6, right? So that's also a flat simplex. You may see this tiling will give you another affine Cox group, which corresponds to the cosmology algebra of G2. And let me say just one word about hyperbolic reflection group, which I think is really a challenging subject. Well, if we consider a discrete group generated by a set of reflections in the hyperbolic space, now, instead of this either Euclidean or sphere, if you consider in this hyperbolic space, then it's rather complicated, I think. So to my best knowledge, it's only classified when on two-dimensional hyperbolic plane or three-dimensional hyperbolic space, which was done by respectively by Poincaré and Andreev in the three-dimension case. So here, for example, is a tiny, you have this H2, two-dimensional hyperbolic space. If you tie it by this the geodesic triangle, where with n is the right triangle, but with one angle is pi over 3, another angle pi over 7. So you may see the sum of these three angles is less than pi. So that means you are doing something in the hyperbolic geometry. So then this will be a hyperbolic reflection group. So what we are doing is we are trying to consider first of all is this reflection group in a Riemannian manifold where with curvature to be section curvature to be non-negative. So let me just first record some very basic results in Riemannian geometry. If we consider a complete Riemannian manifold, which may not be compact, but with non-negative section curvature, then I think a fundamental result due to Chico-Garmore says that this manifold has to be diffeomorphic to a normal bundle over some compact guy, namely the SOR, which is a totally geodesic submanifold. And the whole manifold, the complete manifold has to be a kind of normal bundle, diffeomorphic to a normal bundle of this SOR inside there. So like the topology is really concentrated on this compact, totally geodesic SOR. Okay, so that's the so-called SOR theory. This is probably one of the deepest results in Riemannian geometry. Yeah. So of course there are two issues here. First of all, well, because that's totally geodesic, right? So then that means that the curvature on the SOR is also non-negative, right? So then if you try to study the topology for this non-compact complete manifold, then more or less like you have to like most information is concentrated at least homotopy type is the same as the SOR. Okay. But however the SOR may not be unique, but all different SORs must be isometric to each other and homologous there. So the normal bundle, however, here may be highly non-trivial. So you may have a non-trivial bundle over the SOR, which may admit some non-negative curvature, section curvature. So even like the Poincaré class of for the normal bundle may not be trivial. So that's like some basic thing. So like basic examples, if we consider the manifold in Riemannian manifold with non-negative curvature, of course, as we saw from the SOR theorem, I think the key issue is to try to understand in the compact case. It's mostly difficult, however. Right? And now if we consider compact manifold, positive even curvature, then of course there are some examples, like standard example, like the spherical space form. You have sphere or sphere acted freely by some isometry subgroup of the orthogonal group. Right? Like this is kind of standard example. And except that, I think there are very, very few examples. And now let me just give you a very quick review on this subject, on our knowledge about manifold with non-negative curvature. Like, of course, classical things you can see from any textbook in Riemannian geometry. Like Bodemeyer just tells you that when you have compact manifold with positive curvature, then we know that pi 1 must be finite group, a fundamental group. And also the fundamental group, when the sectional curvature is positive, is either trivial or Z2 when dimension is even. So in even dimension, the fundamental group is very special. It's when the manifold is oriented, actually it has to be trivial. Non-oriented has to be Z2. So that's two only possibility for the fundamental group ever. And in no dimension, we know something. Of course, in two dimension, like Gauss-Bonnet already tells you that the only examples are either S2 or RP2, right? So in three dimensions, thanks to the Fermat's theorem of Hamilton, we know that the manifold has to be spherical space form. like in the example here. That's the only possibility for 3 dimensions. And in general, we have a general theorem due to Gromov, which says that the total Beijing number for the manifold with positive curvature or even non-negative curvature is uniformly bounded, only depending on the dimension. So that means because we have many topologies here, if we take connected sum, you cannot, to make more and more components, and at a certain step, you has to stop because because the Beijing number cannot be too large. And there are kind of finiteness theorem, I think, for the even dimension, basically due to Chigger and Weinstein independently. Namely, in even dimensions, there are only finite many manifold up to Topology, whatever, no assumption on fundamental group, only on this pinching constant. The pinching just means that we have the second curvature to be bounded between two constants, right? Just means our second curvature for the manifold is bounded between 1 and delta, where delta is a positive constant, positive or non-zero constant. So that means if you consider the topology of a manifold with pinched curvature between these two constants, then that means in even dimension you cannot have much difference about the time. However, in all the dimensions, except this spherical space form we just saw, there are many kind of examples which has a highly non-trivial fundamental group. But you may have some non-trivial example, but simply connected one. For example, in 7 dimensions, like Wallach, they indeed constructed infinite many 7-dimensional simply connected manifold, which is just take this homogeneous space. You take SU3 divided by some circle rounded in the maximum torus. Because the maximum torus is 2 dimensions, you take a PQ coprime, then you take a number of infinite many pairs of that guy, and indeed all of these guys were admitted pinched curvature. They even precisely calculated what's the pinching constant there. And of course, the fundamental group is trivial, but the second homotopy group is infinite thickening. Right? But the topology are pairwisely different because the third homotopy group is depending on this PQ. Right? So that means you cannot expect this finiteness theorem of Chigger-Weinstein type. But however, in my joint work with Ron and also independently Petrolin and Tushman, we proved that in all the dimensions, if we consider the pinched manifold, delta pinch, but with pi 2 finite, then there are only finite many guys. So that means we somehow also explain even in all the dimensions you cannot find many examples. It's very difficult to find examples. So now let's go back to try to study what the reflection group on a manifold with a non-negative sectional curvature. Now, okay. So we are considered a discrete group, which means a discrete subgroup in the isometry group of some manifold, where the manifold we assume which has non-negative curvature. Okay. Where the manifold may not be compact but complete. Here I should explain what the reflection means. The reflection I really just means involution, where this involution will have at least one fixed point component which is coordinate 1. Right? But it may contain some lower dimensional fixed point data. But at least we need to assume this involution has a coordinate 1 fixed point set. Okay. We will call this coordinate 1 fixed point component to be a mirror. So that means we may have several different mirrors, but give the same involution. If this guy has a more fixed point component of coordinate 1. Okay. So then we just consider the union of all these possible mirrors. Then we take the complement of that one. That will be the union of the chambers. Okay. So it's clear that the intersection of all the mirrors will be contained in a fixed point set of this group. We will call this group W to be the reflection group for that. Okay, so here, well, because we did not assume anything about the fundamental group of the manifold, even the homological group, right? So that means the mirror may not be separate, the manifold. So you may have like Coleman, even like in the real project space case, you may have like Coleman 1 fixed point set, right? But which does not separate the manifold. So then what we proved is the first theorem we proved is that if we consider a non-negative curve, the manifold, but with a co-compact reflection group, like the group W we talked about, with this action, we proved that this manifold M has to be isometric to a metric product with some Euclidean factor with a saw. The saw is compact. This compared with the previous theorem I talked about, the Chicago-Morse, this saw theorem. Because in the saw theorem, this bundle, right? Because the manifold we know is really a bundle over the saw, but the bundle may be highly non-trivial. But however, if we know the manifold has such a reflection group acting co-compactly, then we know that this manifold even metrically split. You know, that's just, yeah. So the basic input to that one is like two things. One thing is like a work of Yin. He was a student of Chris Kroll in UPenn. Yeah, that was kind of his thesis. He considered the heavens of source because I mentioned the soul may not be unique. So then you consider the union of soul. That's heaven. Okay. So now you consider the heaven. Eventually, in our case, we needed to see the heaven exactly coincide with these whole things because the heaven may be a subset of this complete manifold. Okay. So that's like one key input. Another input is we wanted to say our group is really like a group of polynomial groups. This reflecting group. Then we can use the important theorem due to Gromov. We say this group has to be virtually nilpotent, means it has to currently a finite index subgroup.
So the soul is compact?
Soul is compact, yes.
And the isometry group, how is it acting on the other factor, on the RK factor?
Okay, that's a very nice question. That's just product. Like you have two. One thing acts on this RL, which is just like a Euclidean reflection group. So like a fine constant group, right? You have something, I will come to that point, right? So that's our manifold has to be split. So then, in that one, then our reflection group will be a product of something, W1 X, where W1 will X on this factor.
By ordinary reflection.
Yeah, by the Euclidean reflection. Okay. So another factor we wanted to use is Gromov's theorem, which was conjectured by Tits, Merman Tits, right? Okay. So that's the first one. And as a matter of fact, we can say something about the manifold structure in general. So in this case, we can say that up to final cover, our original manifold M, up to final cover, we can say that the orbital space to a unification of that group, because we have group action, W acting there, right? Now we can give this group but final cover, say M hat, we can have an action there. And then over there we can say very precise to what is the orbital space. The orbital space just plays the role for the fundamental tempo for the group action here. So like the orbital space in that case must be a product of either some delta i's, which I call that's like Euclidean one, like that one, because this guy may not be irreducible. You may be like a reducible one, right? You may have something like that. Or this each xi may be some spherical one, or in the worst case, maybe you have a silver phase where meet together. That means like for that particular component means the fixed point set is non-empty for that component group. So that's the structure for that. For the manifold equivalent topology. Okay. So motivated by this, we will call such a reflection group action is locally indecomposable, right? That's like a core case, right? Like Marston. So if the open space I call it not isometric to the product of two guys by the balanced product by x cross y divided by some final group acting on the product. So in that case, I would call it locally indecomposable. So actually, the classification were reduced to the indecomposable case. So in that case, we can say very precise. For example, now we start with some A manifold like that is non-negative curve with compact action. And if we say this orbit space is indecompressible and not all mirror were made together, that just means the fixed point set is empty. Means the reflecting group has no fixed point. So that would imply the manifold has to be equivalent to one of these four standard cases. Either is a finite space or finite towers with such a standard linear action on that, or it's either sphere or RPN or real projective space with a standard spherical reflection group acting on that one. So this will give us a clear picture to what should be the reflections and groups. Okay. So as a remark, actually the open space in one of the cases is easy, right? Then that must be piecewise linear homomorphic to either a Euclidean simplex or spherical simplex. Like in the last two cases where it is spherical simplex, you can put a constant curvature 1 metric on that. And in the previous two cases is like flat. Right. So from here, start from here, we can have a clear picture for the group, for the reflection group. So we can generalize somehow, because the previous theorem says exactly means the case not all of the mirror were made together. Well, a complement case where it is that if some mirror were all mirror were made, right? So in that case we can also get some kind of structure, but because I don't have much time, so maybe I will skip the results like that. Okay. So finally, we can say that this reflecting group we talk about has to be like that. It's either a quotient of W hat, where W hat will be a direct product of finite remaining either affine Cox groups or spherical Cox groups. And this C is an elementary to a Billing group in the center, because for some spherical Cox group, it may have C2 center, like C type or E type or EA type, for example. Right? So, for example, here is a table for that. Of course, Strata knows that very well. Yeah, like a spherical Cox group. This is a table I copied from Fuquan. Right? Like you have this really this ABG type and segment type, and the last three are not crystallographic Cox group. Actually, doesn't appear in our case. And this is for irreducible one, and that's a fine Cox group. That must be one of these. Yes, that one. And for the affine one, where each one will correspond to one Casmodi algebra, where we can be realized there. And so our group, in summary, we say our group W will be a quotient of this W hat by some central element, where W hat will be a product of this guy. So that's a clear picture to all of the group. Okay. So as a matter of fact, actually, I just mentioned for the hyperbolic reflecting group is a very tough subject, right? Because I think a very famous theorem said, Weinberg says that even the dimension for the simplex is very high. It's higher than 29. Then you cannot have such kind of compact hyperbolic reflecting group. If you know dimension, I think it's a quite important problem to ask whether this reflecting group can be Gromov hyperbolic. This kind of a problem is difficult actually in the theory. Okay. So now let's try to move, because we are geometry. I tried to study manifold, right? I'm not really interested in discrete group. So let's move from this discrete one to Lie group. I really consider the Lie group action on the manifold. That's what our real purpose. Okay. Now let's come to one concept, so-called polar action. We consider a complete Riemannian manifold. We consider a connected Lie group, say G. We call this action to be polar. Just means that you may have some connected, complete submanifold sigma, which is immersed, such that the sigma will meet every orbit of the action. That just means that one. The second means whenever this sigma will meet the orbit, it's always meet in the perpendicular way. Means it's always perpendicular. So of course, this at one point is perpendicular, right? Then will meet everywhere perpendicular. Just like you take a normal to that, where it's always normal to everywhere, every orbit, because the action is isometric action. So this is kind of action we are considering. The motivation I will mention later on is basically back to knee theory. Yeah. So here I will call this submanifold to be a section, and in the particular case when this guy is flat, sigma is flat, we will call it hypercolumn action. Okay. So associated to this action, there are two things which is very, very familiar, like in the knee group theory. First, we take something so-called a polar group, which is just take the normalizer, the stabilizer of the of this section. Just means you take all element in the group G, which fix this section, where it keeps the section invariant. Then you divide it by the kernel of the action on the section. Then take the quotient, which will be so-called polar group. I mean, in the knee theory, this is exactly to be the Y group we consider. If we consider the maximum torque to be sigma, then that's what we consider. Yeah. And by the way, this terminology was introduced maybe first by Fuquan and Julian Turin. Yeah. Okay. So as a matter of fact, this section is always totally to that. So that means if you have any curvature property, like for the curvature, section curvature is non-negative, for example, then the section will share the same property for the curvature. That's nice. Okay. Okay. Let's come to some easy example. Namely, if you consider the rotation of the circle acting on the two spheres with two fixed points, namely the north and the south pole, the section will be exactly the correct circle pass through these two poles. And the polar group we talk about is just the Z2 group, or the 2. And any cohomogeneity 1 action will be polar. The cohomogeneity 1 just means you have a compact knee group action where the principal orbit is codimension 1, or the orbit space is one-dimensional. Because if you get any normal geodesic to one principal orbit, will continue everywhere where meet the orbit. And if we consider compact knee group acting on its knee algebra as the adjoint action, then this will be a polar action, standard linear polar action, where the section will be the maximum abelian subalgebra in the knee algebra. And this polar group pi we talk about is the usual Y group. So that's why this concept is a generalization of that kind of knee theory for the adjoint action. Yeah, that's another example. If you talk about taking the orthogonal group, which is acting on the symmetric n by n matrices through the conjugation. This is once again, this section will be exactly the diagonal matrices. And the polar group is like the permutation group in n letters. So that's standard examples. Okay. So a famous result to the Dada says that if you have a compact representation, like take a compact knee group, take a representation which is polar, we just consider this as an action. We just consider this one as an action on a linear action. On the unit sphere, you consider the linear action on the sphere. Right. And this action is polar, because in the terminology I just talked about, then he completely classified what should be that representation. If you consider this linear one, this is linear action. And his result says that, okay, this action is nothing else, and orbit equivalent to the isotropic representation of a symmetric space. That means you have this action where it comes from like U divided by G. That's a symmetric space. Symmetric space. And then for symmetric space, of course, G will acting on the tangent space as the identity. And when you restrict it to the sphere, this will be the action And what Database theorem says that whatever this representation, which is polar, is more or less orbit equivalent. I don't want to bother you to introduce that terminology, but more or less just say this action has to be come from this aspect representation of symmetric space. So that gives you a complete picture for the linear polar action. Okay. What do we prove in the work with Custom and Goodenough? We proved that it's the following. If we consider a manifold with positive curvature, we have a polar action. And the manifold is simply connected, where we have the cohomogeneity is at least 2. Like we will exclude the cohomogeneity 1 case. Then we can prove that the manifold has to be invariantly linear, isomorphic to one of the standard ones. It's either on the sphere, like in the Database theorem, or in the quotient, in this rank 1 symmetric space. So this theorem can be regarded as a nonlinear version of Database theorem, because Database says that if you have a linear action which is polar, then it has to become from symmetric representation, isotropic representation of a symmetric space. What our theorem really says that you can draw then a linear condition. You just say that you start with some unknown manifold, but with positive section curvature. Then if the principal orbit has coordinate at least 2, then you can say it has to be linear, and it has to be the representation comes from linear representation. That one. Okay. So this for cohomogeneity 1, this guy is never be true. So that means that you have no space to improve that, because there are many examples. Like for example, most of the alpha, one of the example we talk about actually mean isometric cohomogeneity 1 action, which of course is not like that type. Right? And also, it has to be an important theme actually for geometers try to construct cohomogeneity 1 manifold with a positive curvature or positive Einstein metric, right? So then, of course, that's a natural question whether one could use this polar action instead of cohomogeneity 1 to construct more examples. That was the original motivation to prove such theorem. So actually, our theorem just breaks the drill. So that means you have no way to construct a new example in high cohomogeneity by using polar action. Okay. So now let's move to the third topic of this talk. Okay, that's also the machinery. How can we prove such kind of thing in geometry? Actually, I think no classical method in Riemannian geometry can work with that one. That's so. So we need to use the Tits gradient geometry. So Tits geometry really a generalization of Tits gradient. Okay. So roughly speaking, Tits gradient is really just a simplicial complex, which is a union of many subcomplexes we call a parliament. Like we have a building, we have many apartments. And which satisfies a few axioms. I don't want to bother you now what the axiom is, but rather than I give you some examples. A Cox complex, right? Like this subdivision of this sphere by this fundamental domain of the Cox group on the sphere, for example, which gives you a scene Tits gradient. I call scene by the terminology of Tits. And also a projective geometry over any field K is a spherical gradient of A type. Actually, the motivation for Tits is exactly trying to generalize this projective geometry to correspond more geometric object, and then using this geometric object to study group theory, particularly for the simple group. Okay, so in fact, you can see this a little bit more precise if you consider a vector space, say n plus 1 dimension over the field K. Now you consider just a flat complex, which will be the projective geometry, for example, here, where the simplices will be the chain of these subspaces, and the chamber will be the maximum one. You just consider like 1 dimensional, 2 dimensional, and so on. This maximum flag will give you a chamber like the maximum dimensional subcomplex there. Okay. So the vertices for this chamber complex will corresponding will be named or neighbored as points, lines, and planes, and so on in the project geometry, which will be a type for that, for the vertices. Okay. And also a rank 2 building is a simple. A rank 2 building is nothing else, just a bipartite graph. You have just like a graph. And also another very important example, and plays a very important role in that in Riemannian geometry. Like if you have a symmetric space of non-compact type, say G over K. Instead of that one, now we consider a non-compact type. Say G is non-compact one, K is the maximum compact subgroup, where you may consider the abstract representation for that one, and that one, the infinity for that symmetric space will be spherical building. Yeah, actually, the Burns special exactly use this to reprove a theorem of Bauman about the characterization of symmetric space of rank at least 2. Okay. So, geometrically say that a spherical building is just a cat 1 geodesic space, where every link is always a building, because the building is just like a simpler complex. Now you can talk about the link to the vertex. So every link to the vertex will be a building, and which is a cat 1 space. The cat 1 just in terms of this comparison sense. Okay, so a very important theorem due to Tits says that a Tits building of a rank at least 3 are in 1-to-1 correspondence to isotropic algebraic group over the field K. So that means for whatever this combinatorial object Tits building, you will get some algebra. So for every building, for this rank condition, you will get some field and get an algebraic group over that field. So that's I think a very important theory due to Tits. Okay. So now let's move back. We have just warm up a little bit with this abstract theory of Tits. Now let's move back. What's our idea? How can we try to use this Tits building to study our original problem here? Okay. A very easy actually, quite easy theorem. Lemma Fuquan Fang says that if you have a polar action, no curvature assumption. Okay. Then you can say every slice representation will be polar representation. Okay. So that means according to Dada, we say this will give us something related to symmetric space, because for whatever such a polar representation, you will have a symmetric space associated to that guy. That's what. Okay. So that's what I just mentioned here. So associated to this symmetric space, then I just mentioned already, you have a spherical building of subcomplex, which is a spherical building. So that's right. Okay. So another lemma due to these two guys, one Brazilian guy, they proved that okay, if you have a simply connected polar manifold, right, and then the polar group we talk about is just a reflecting group on one section. So that's why I first, at the very beginning, I have to talk about the reflection groups. So then really, in order to study this polar action on the manifold, we really needed to study that reflecting group on the section. Okay. So in the particular case, because at the beginning I talked about the section, the manifold with reflection is non-negative curvature. But here we're sticking to the positive curvature. So in this case, you can say more precise and simplifies actually. So in this case, we can say the section has to be either the sphere or real projective space. And the group pi, we talk about the polar group has to be crystallographic Cox group, or is quotient by Z2. So the proof to that one is really just a concavity for the distance function in the Riemannian geometry for positive curvature. Okay. So motivated by this, we can make a definition. Right? We say such a polar action is irreducible or reducible. Really depends on whether this Cox group acting on the section sigma, which is linear, because we know it's already linear action. Topological linear action is irreducible or reducible. So Yeah, that's easy to say. Okay, so follow this, we can associate to such a polar action, we can associate to a so-called temporal system, which is really a Tits geometry, something more general than Tits building. Now record that we have an action, which is where with the orbit space there's something like stuff. Here we have something system there. So you may regard, because the assumption we know that as a set, this guy will be the union of our orbit of T as curve, where delta will be a fundamental tempo in one section. So now we have something like we have a simplicial complex where with a temporal transitive action by the group G. So this guy will be a temporal system, because we can define a so-called adjacency relation on this simplicial complex, on this complex, and this will give us a temporal system. I don't want to give you too much detail about it. Okay. So now on this one, record that this as a set, they are the same. Now I want to introduce a new distance on this one. Namely, we will want to introduce the horizontal distance on this one. Because there was a Riemann metric distance. Now we counting 2 points, say PQ in this space, just counting how far you can go from P to Q by the horizontal geodesy. Namely, we take the infimum over this the curve gamma, which is perpendicular to your orbit, to your T orbit. Okay. This looks like a sub-Riemann geometry. Like we really need to look at the curve, which is perpendicular to the orbit. Okay. So now with this new metric, there is a new topology, namely the same topology on this one. Now we want to consider the same topology on here. Namely, I wanted to denote this temporal system, so get as this C, Mg, which may not be a building, but however ever need, it's really just a building because it comes from the semester station. So now we want to consider the universal cover for this guy. I just like to consider the universal cover, namely Jirdan. This is a confusing for the notation because our many-body, we record that our many-body is really semi-connected. Maybe this is at that time. So I would write this guy as a set. This guy is coincide with many. But now we introduce a new topology. We consider the universal cover for this new topology. Okay. So here, for the new topology, because that's universal cover, so you've got a vector acting freely here with quotient to be the original one. Okay. So a very important theorem to the Tits said that, well, if you have a temporal system, range is at least 4, for example, which is simply connected and simply connected, there must be Tits building. That means the universal cover is a Tits building. Okay. So once this guy is a Tits building, we know that it's kind of thing associated to a group, algebraic group. You have some algebraic group acting on that one. Okay. So now, first of all, we have to show this guy is connected as a temporal system. In a sense, every 2 points can be joined by some horizontal curve. So that's basically based on one connectedness theorem due to Wilton. From there, we can say that for any 2 chambers, like any 2 chambers in this same topology can be joined by a gallery. You can reach from one chamber here to another chamber by a fleet of chambers. Namely, you can, in other words, any 2 points can be joined by a horizontal curve. You find the distance. Okay, so based on that, because we got a connected space, connected topology, we can talk about the universal cover is also connected. Now, universal cover is simply connected in the sense of Tits, because that topology should coincide with the usual simplicial topology we talk about. So then, this guy will be a Tits building if the range is at least 4. Okay. So now I wanted to go back to our original topology, manifold topology. Right? Because we know that over this guy, there is another manifold topology, where every vertex is where the homogeneous space. We have a scene. But on the scene topology, we call that every orbit will be regarded as a discrete point instead of. So that's a huge space considered as a discrete topology. Because now you just regard disregard the topology, regard every homogeneous space as a discrete space. Okay. So now I wanted to prove back, because of here there is covering, so you have this projection map. Now I wanted to prove back this hostile topology, this sick topology here, pull back to this covering space to give this guy a new topology, a sick topology. Okay. So then that's a key issue. That I wanted to say, well, we could give this guy a sick topology so that this one is the topological building in the sense of verse specific. Okay. So with the sick topology, we can say that, okay, this group, that group, it was regarded as a discrete group. But however, as a sick topology, this guy will be compact group for the sick topology. Okay. So actually, a similar idea was used independently by Alex Nichak to study the Polar foliations on symmetric space. To use this covering idea. Okay. So a result of Bert's specific says that if we have a topological building, in a sense, we have a second topology. I did not make it very concrete, but it's something, that one has to be equivalent homeomorphic to a sphere with where the action will be, the chamber system will be just exactly comes from the example like the theorem of Dada. That means this, as a topological building, the topology on this guy will be exactly coincide with the sphere, and the action will be linear at the point. Okay. So as a result, that means this guy will be a sphere for the sixth topology. This guy will be the sphere of some dimension. And with this group will be compact group acting freely, so then there is no choice. This group has to be either trivial group S1 or S3. Recall that this was regarded as how we get the group was regarded as a discrete one. We constructed from discrete one. Then we get a new topology. So that's for the group. And for the action, because there was an original action here, right? And this action can be given as a covering space to the action of something that is insured on that one. And this action in jihad or jitirda will be a compact group for the sixth topology, for the compact open topology for that. On that one will be a compact group. So the action will reduce from this jitirda to G. So that's what I mean. This G action gives to a compact new group action on a sphere, and with quotient to be G. So put it all together, this is where it implies actually the theorem I talked about, namely where a special case. I should say a special case. This building accrues where it implies where the case is irreducible. What I talked about, where when the rank is at least 4. That's because the Tits theorem needed to assume the rank is at least 4. So in other words, it's equivalent to say the dimension for the orbit space is at least 3. So that was the basic idea. And also we have to deal with two remaining cases, namely like an irreducible one, where the cohomogeneity is 2, or reducible one, where you clearly actually may even have a fixed point. That's like some additional work we have to do. Okay. So what can we do next? Okay. Because we just talked about we have action on, we classified all of these polar action on a manifold with positive curvature. However, it's a natural question. How about the case where even with a manifold, M just means curvature non-negative? Right? With polar action, we would like to classify that one where so that the section curvature is just non-negative. Of course, we know there are many examples, right? every symmetric space, right, every knee group, the bi-American metric on that will have a non-negative curvature. So that means, topology for this guy must be very, very complicated. There are more candidates. Even every product of that one will be that, and so on. Many. You can construct tons of examples. That's very different from the positive curvature case. Okay. So the basic conjecture, we would like to say that, okay, once you have this action on compact manifold with a section curvature non-negative, say what I talk about a special case, namely the section is flat, is tau. Recall that, namely sigma is tau. Actually, this is a typical case and also the most important case. Recall that in the previous reflection, in the previous section I talked about when we have a reflecting group acting, right? Recall that we have, I also call M there, we have some reflecting group acting there, where when we say if this guy is indecomposable, right, and not all mirror will meet together, then there are only 4 cases. Either this guy will be sphere or will present space, or is a flat torus or Euclidean space. So this is really just a typical and most important case, actually. Okay. So in this case, we call it, if this is indecomposable and the hyperpolar just means the sigma is torus, then we would like to say that this M can be covered by a D group, some D group say U, D group. Then your action here can be limited to some action there. And this action will be exactly the symmetric, corresponding to symmetric space. Like a joint action or of the knee group on that from there. So basically we would like to say whatever this polar action on a manifold like that, where when the setting is given, like in hyperpolar, setting is flat, where we're corresponding to something from symmetric space. Because whenever the converse is obvious, whenever you have symmetric space, when you take the action of G, for example, you take the symmetric space, G over K, right? You consider the symmetric space. Then you take this action from another side, right? Say K from right side, the G from the left side, another side. So then this action will be polar, and in particular case, let's say you take a H1 action, right? Take a C inverse, take a H, right? G, right? And this one will be polar action with respect to my invariant metric, and where the section will be the maximum power, where the section sigma will be the maximum power. Yeah. So what we would like is we would like to have the inverse, namely, because of course for the bi-invariant metric we know the curvature is non-negative. So now we say that we can forget about the curvature, the group structure. You need only say the curvature is non-negative. You have such a polar action with flat torus, then it has to be something from there. Okay, we like to say then you must have some group structure. This kind of rigidity here. Okay, how can we do? That's much more complicated. Must be. Okay, so next, so there is something corresponding to spherical building in Tits theory in so-called affine building, which is much more complicated. Now let me just give you one example to see. We just consider a very simple knee group, take SU3, and we take the adjoint action of SU3 on either third. We take SU3, which is acting on SU3 by such kind of adjoint action, then you just take H2, H inverse, where this SU3, right? And this action, of course, is a kind of polar action, and the maximum power is T2 over there, where is our section, which is perpendicular to every adjoint orbit of this action. Okay, so now we can have consider we will have a temporal system again we just consider this SU3 as a unit of these Y chambers, or T, SU3. The delta is just one Y chamber in the torus. So then we have such a chamber system, I denoted there. Then we can consider the universal curvature, that one. Okay. So that's just final dimensional thing. Now, I mean that, yeah, we call something say delta there. Okay. So this guy where the Tits theory also applies. That's a very big, powerful machinery. The Tits theory says, well, even for this kind of thing, chamber system, the universal cover is again a building if the rank is at least 4. Okay. So now once again we get a Tits building. But however, this is a affine building. Here I generated by another one. It's it's A2 type, and also the cost group there is just the tiny of R2 by the flat equilateral triangle. Okay. But however, this guy record that is really infinite dimensional. Now it's a complication coming up. This really comes from Casimodi algebra, from algebraic group, actually. And okay, so however, this space as a affine building is really a cat zero space. Now if you consider the metric on this guy, which is really just a cat zero space, because every apartment will be, you can see over here, the maximum torus looks like the section, and then over here, the section will be equal to every R2. So over here, in the building, in this affine building, the section will be flat 2 plane over there. So that's a cat zero space. So the nice thing is that, and also interesting thing is that now we started with something with non-negative curvature, but we reached something with a kind of non-positive curvature. Okay, that's a cat zero space. Okay, so now we would like to say that, well, we need to understand this one, this cat zero space, and to say that to get an equivariant classification up to under this deck group action, because we have deck group action there, we try to classify the coordinate space, because the coordinate space by this one will be our original group, right? Like, of course, here we start with just this example. And in the example, actually, you can see this universal cover, this guy, can be regarded as the free loop group action on the loop algebra. So that's a Casimodi group. And it's interesting to know, as I said, this guy is really just a cat zero space. So, yeah, so I think it's still far away. We get something by using this building theory in a certain case, but I think it's still far away. How can whether we can prove the conjecture I mentioned there? I think it's still under working. Yeah. Okay. So in general, maybe let me just mention a few sentences. Yeah, the affine building were corresponding to algebraic group over a local field. Why? That's much more complicated. And in our case, the local field, actually we can prove that is not locally compact, but the local field will be, in our case, we can prove that our local field will be like the form on the Roman series, like over C of T. Yeah. So what we have to study the algebraic group over this local field, and also we needed to study the subgroup, like this deck group, how the deck group behavior as a subgroup of an algebraic group over this kind of huge field. So I think that's something related, very related to Casimodi theory over the real and complex and so on. So I think that's it. Thank you so much.
Questions, comments?
So you say that's an infinite dimensional.
Infinite dimensional.
That's sort of like a loop.
Yeah, right. Yes. And indeed, that's in general, what we can say, actually, maybe I could say a little bit more words. Namely, we start with some channel system, T, right? And now we got universal power in this case. And then Python group count. And right. And this one, for example, in the in delta K, in the affine for the affine constant group, in that case, we know that this building will be corresponding to this algebraic group, say, okay, M1 over the field, say, C. And this will be the full automorphism group acting on the building. And our group, we call that we have group action there. We can have something unit action, and our teacher in a subgroup there. And this is actually a loop group. Yeah.
Did you finish? The previous slide you said about SU
Yes.
3,
Yes.
which is rank 2 in
Okay.
finite dimensional.
Yes.
It was related to the affine type A2, which is rank 3, I believe.
Sorry, which one?
A2 tilde.
A2 tilde.
It's rank.
But as a fine building is a rank 2 building. Yeah.
You said you needed the rank to be at least 4 in order.
No. Sorry. For the theorem, you need that. But this is an
this is
example.
not rank 4.
You're right. Yeah. Thank you. Yeah. But this is just an example. What I mean is here is one example. In this particular example, you can construct that. What I mean, the Tits general theorem says that for whatever chamber system, like we started with some arbitrary, this kind of manifold with some kind of Poynting action, then the universal power has to be a building if the rank is at least 4, right? Right. Yeah. So, but in this particular example, we can construct what the universal power is. Yeah.
So is anything serious known about polar actions for the for Kac-Moody groups, for affine and for higher types?
Basically, no. I think, I think one thing is one should ask whether one could have a similar result like Dada, because Dada really considers a linear representation, right? On the linear representation by finite group, B group, which is the bottom. You may ask whether Dada theorem can be generalized to Kac-Moody group acting on cubic space, right? And it's unknown. But one related thing is I think Heinz and with one Chinese, with Xiaobo Liu, they have a paper in honors. Heinz, yeah.
You mean
for the
professor in Dortmund?
in Augsburg.
Augsburg, right.
Yeah.
His student is Walter Frame.
Yeah.
He did some work on affine buildings.
Right. But I think not Frame didn't do much. I think didn't work out much. But I think in Heinz, the paper Heinz with Liu in the honors, they proved that if you have a dimension at least 3, like this isoperimetric submanifold, which has to be homogeneous. It's a kind of a similar flavor as Dada's theorem, but it's not a complete version. I think one very open problem is whether Dada's theorem is true for Kac-Moody group action. It's not known yet. And also, like this burst specific work for this finite spherical building, whether it's true for this affine building, is not known. I think a few weeks ago, I invited Prasa we had some discussion on that. We are trying to see whether we can do something.
Yeah. What if is there where we have this positively curved manifold transaction? If it was strictly quarter inch, could you apply the Ricci flow to it and use it as regular?
Yeah, I mean, even you don't have to ask, okay, I see. Using Ricci flow, you can always develop, right, to Yeah, I think so. That's right. I think, yeah, if you have a quarter Beijing, then the action has to be linear. If you have an isometry, then you will preserve the isometry, then you can eventually say that it has to be linear, I think.
Questions? Fingers speaking.